Alright, silly people, here's the situation. Uh, First, we're meant to find uh, if or if not the determinant of this sigma dot A matrix is invariant under the transformation given there. It's pretty much a rotation. So, first part's pretty easy. Uh, the determinant of sigma dot A, I'll write like this, and then not elaborate on its form at all we have to show is that if we take the determinant of the other stuff, it's this, right? So just looking at that, sigma dot a prime will be the determinant of all of that junk up there. I just copy that down. So cool thing about um, determinants when you're multiplying multiple matrices together is that you can just split up the determinants as a linear combination. So you're literally just going. You're literally just saying, do this determinant and do this determinant and do this determinant all separately. Um, and then you can also reorder that because these are all scalars now. So now you have sigma dot a there, and then gonna put these guys next to each other for no particular reason, because we're gonna evaluate each determinant separately. Right? So whenever you take the determinant in this case will be the same as doing a square modulus. Uh, so that means taking the square root of the complex conjugate multiplied by the thing in the uh, braces. So I don't know why I wrote the absolute value line so big there. The first one is so complex conjugate will have a minus I sigma dot n hat phi over 2 times a positive I stuff under a radical. And then the second or the third determinant will be like the same shit. Ugh. Same guy. Um, those are both 1. You have a minus exponent times a positive exponent of the same stuff. So that's going to be 1. That's going to be 1. So the determinant is invariant. Next bit. It's telling you to find what AK prime is. What is even AK? Well, you can express the dot product of a Pauli vector with any other vector as being sigma k AK, just because each component of the vector presumably is just a scalar component. Um, so you're multiplying that by Pauli matrices and summing over k. Um, which means sigma dot a prime can be written as sigma k ak prime. Now we're meant to find what ak prime is. We're looking at sigma k ak prime. which is going to be exp I sigma dot n hat phi over 2 times sigma dot a, which you can go ahead and index that. That'll be sigma k ak, then the other stuff minus sign over 2, right? So, and then the problem does specify that we're doing n hat is in the z direction. So n hat, I'm going to rewrite as z hat. So the sigma here is a Pauli vector. So if z hat is your vector that you're dotting it with, then you're just going to end up with sigma 3. So you have exp I phi over 2 sigma 3 times sigma k ak exp I minus phi over 2 sigma 3. All right. Now you can do your Euler identity. Interestingly, when you do it on something which involves e to the matrix of some kind, that turns into multiplying the sign component, the imaginary component, by the matrix. So that's sine phi over 2 sigma k ak exp, nope, Euler identity that bitch, minus I sigma 3 sine phi over 2. All right. So just kind of multiplying all that through. I'm going to leave AK on the outside. We're kind of just foiling. AK times cosine squared phi over 2. Okay, I'm going to put the matrices first. So it's sigma k cosine squared phi over 2. Minus I sigma k sigma 3 times cosine phi over 2 sine phi over 2 plus I sigma k sigma 3 cosine phi over 2 sine phi over 2 plus I squared is minus 1, so it's plus. It's sigma 3 sigma k sigma 3. Okay. Sure. And then that's meant to be multiplied by stuff. Plus sigma k sigma 3 sigma k sigma 3. Yes. Times sine squared phi over 2. Be careful, silly people. You're meant to keep the order of the matrices whenever you multiply them through. I wrote this, the third term is sigma k sigma 3. You're meant to write it as sigma 3 sigma k so that you end up with a commutator. We got there in the end. So, for Pauli matrices, if you left multiply and right multiply by sigma 3, you just get minus whatever is in the middle. And then the other stuff becomes a commutator. So now you're looking at sigma k ak prime is ak. Sigma k, you have cosine squared phi over 2 minus sine squared phi over 2. plus I cosine phi over 2 sine phi over 2. It's the commutator of sigma k with sigma 3. Right. All right. That's the commutator for the polymatrices. At this point, it's worth specifying which k you're looking at. So k equals 1, k equals 2, k equals 3, because that's how we're going to get our commutator, whatever it's going to be. So let's look at k equals 1 first. Hello. K equals 1. So sigma k a1 prime is sigma 1 a1 prime, I should say, is a1 times sigma 1 cosine squared phi over 2. Yeah, that's cosine phi. And then that is just 2i cosine phi over 2 sine phi over 2. Actually throwing a I squared onto it, times sigma 3, because it's 1, 3, 2. No, it's 2. Sigma 2. Simplifying that, that's going to be a1 sigma 1 cos phi plus or minus 2 sine phi sigma 2. Actually, it's just single sine phi, so just minus that. You can put this into a matrix form. So you'll have a minus I sine phi. No, that's not right. Nothing in that element. This one is cosine phi minus I sine phi. This one is cosine phi plus I sine phi 0. So it's kind of just a rotation. And if you do the same with any of the other k's, you're going to find that you're just doing a rotation on each of these. So if you want to write it out explicitly, the whole rotation matrix should be cosine phi sine phi minus sine phi cosine phi 0, 0, 0, 0, 1 times this stuff. All right.